It's really exciting to be here in terms of, I think, a city that exemplifies what the future can be. It definitely is Singapore. It is such a beautiful city. I'm from San Francisco. I'll give you a background on MemSQL, but I'm incredibly excited to be in Singapore every time I can visit, and it's just because it really is just a phenomenal city. And we'll touch on what every city should be. And I think if more cities could move as quickly as Singapore in sort of adopting initiatives, I think the world would be a better place. And what we're going to do then is basically build an application today. And it'll be very exciting, so we'll get into the technicalities pretty quickly. But to give you a background on MemSQL, I'm one of the co-founders. Started the company out of Facebook in early 2011. The idea was to enable every company to be a real-time enterprise. We saw a lot of big data problems at Facebook being solved years in advance. And we realized that in-memory technology was the next phase for big data. If you look at Hadoop, it really has solved the volume aspect of big data, but the velocity and the variety is still there to be tackled. And we believe in-memory technology is a phenomenally important way to do that. So that's just the background on the company. But I wanted to ask you guys, what does a smart city look like? I think we can definitely have a conception of what it looks like. It's definitely something that is futuristic, it's ultra clean. For some reason, there's always highways that loop around buildings for some reason. But that is our conception of what a smart, futuristic city looks like. But here's the reality. We have a population of more than 3 billion people going into cities. And unfortunately, very few cities can actually enact the type of advances that are necessary. And so we're working with our reality. As I mentioned, 3.9 billion people live in cities today. By 2050, we'll add another 2.5 billion people into cities. So as we think about what a smart city can be, it's super critical that we nail it now. Because for the next few decades, we're going to be adding billions of people into urban centers. And fundamentally, we're here to talk about smart connected cities to create sustainable cities. And we can use technology to help us get there. Because fundamentally, what we don't live is in Tomorrowland. We live here. And we really need to think about how we can design cities and use technology to help people and to go beyond the technical or technology and really deliver real value to billions of people worldwide. Now, the good news is that the technology of today can build smart cities. We have an ability to use what we have in our current ecosystem around Hadoop, around data warehouses, around streaming, around in-memory, to really deliver phenomenal technology at a city-level scale so that we can improve people's lives. And we can start about what should a smart city have. We saw that first photo, what a conception it might be. But realistically, what does it mean to have a smart city? Well, I think a smart city should have citywide Wi-Fi. It needs to basically have an ability for anyone in that city to connect for free. And more importantly, as we delve into this demonstration, to let any device connect to the internet. I think we're in a very interesting space of big data and a space of our times where we really start to consider that internet is a fundamental human right. The ability to communicate, to share ideas, to span countries, to span cities. The internet should be available for all. And we're seeing some initiatives across the world where internet is offered for free. But we really have to blanket cities fundamentally from a technical perspective to build applications that we'll show you today. I think every city should have an application. The ability to get smartphones into billions of people's hands is coming. And the ability to log into your app and report issues, potholes, etc., is just one example of why every city should have an application and to use that with the Wi-Fi. But as we look into sort of what happens with data itself, we are citizens of any given city, and that data belongs to the public. Therefore, it's incumbent upon the city itself to make that data available. You can think of that as an open data initiative. San Francisco, where I hail from, does a phenomenal job of giving that data to the community for use. And I think it's something where, as we look at what a smart city should become, it means sharing data so everyone can access it. But most importantly, I think every city that is serious about building a smart and connected city needs to have an adaptive, fast-moving IT department. The notion of IT moving very slowly is obviously well established, But if we want to get our public sector moving quickly, we have to empower cities with budgets that let them essentially hire great developers like yourselves to work for the city and build applications that change people's lives. So at a high level, I'm sure we could come up with a lot of other great ideas about how smart cities should work, but this is just a high-level brushstroke of what a smart city might look like. And now it's time to learn how. So we're going to jump into an application that's called MemCity. This application is going to be designed to capture 1.4 million households data, capturing 8 devices in each home every minute. And what this will do is let us pump 186,000 transactions per second from Kafka to Spark to MemSQL. Now, this is a lot of information. It's a lot of data. But as you saw earlier, it's actually very cheap to run this because of the cloud, of Amazon itself, of other clouds. This is only costing $2.35 an hour USD to run, which means that you're looking at about 20,000 USD to run this type of infrastructure for a city. So very cost affordable. And I think it's a great way to demonstrate that big data can be empowering to more than just big companies. So as I mentioned, 1.4 million households, 8 devices per household, and 186,000 instances per second. And we're going to use something called the real-time trinity, Kafka, Spark, and MemSQL working together. And this is going to enable us to avoid disk as we build this application. I think disk is the greatest enemy of real-time. This is why we have memory-oriented architectures right there. And it's fundamentally because disk is glacially slow. If you were to compare the timescales between memory, SSD, and disk, you might consider an example of going to the library. If you go to the library and you grab a book, I guess that's already outdated. Who does that anymore? But suppose you were to go to a building to find a piece of information. That would be equivalent to going and accessing your memory on the server. If you wanted to go and access some information on disk, well, all you have to do is go to the harbor here, hop on one of those barges that we all see, and then wait 2 weeks to cross the Pacific, get to California, look up the information in that library, and then travel back another 2 weeks. So that type of time scale is what is prohibiting real-time applications from working. Disk is a phenomenal way to store lots of data, but not a great way to access it quickly. And most of the problems with databases from the 70s onward have been focused about how can you actually balance reads and writes happening together. So what we'll talk about next is how to design that real-time pipeline. And what you'll find is that this real-time pipeline can be applied across any type of application or use case. So in this particular example today, we'll be talking about smart cities and how to leverage this with IoT. But you can use this for a variety of applications. We'll jump into some examples next. But we'll start off with Kafka, then move to Spark, and then to MemSQL. And the whole goal here is to offer an end-to-end data pipeline in under 1 second. Kafka, for those of you not aware of it, it's a very popular mainstream message queue. You can subscribe to topics inside of Kafka, and you can think of it as the centralized data transport for your business. It's open source. There's a lot of support around it, and it definitely is going to be the message queue to win. So I would highly recommend everyone here to start researching and learning about Kafka, because it's going to be a very, very powerful technology. Now, we all know about Spark, of course. It's an in-memory execution engine, not a database. It's transient, very good for high-level operations, programmatic logic. You're manipulating data. You have your custom model here. You're doing something that isn't necessarily expressible in a conventional declarative language like SQL. You're doing machine learning. You're doing an ability to model anything you would prefer inside of this environment. But of course, because it's transient, you need to put that data somewhere. And MemSQL as an in-memory database, also community edition, free and unlimited scale, gives you the ability to store your state of the model and capture that data and basically build applications because you have a SQL interface to this data streaming in. So what we'll do next is actually go ahead and build that application. We're going to walk you through how it works to basically collect 1.4 million households worth of data and get it into your infrastructure very quickly. So we're going to subscribe to Kafka. Kafka is basically will serialize the data. In this particular instance, we're working with a little event that has a date, time, some information that we needed to resolve, and we're going to do that next. So we publish it to the Kafka topic. You see it gets zipped up, serialized, and then it's added to the event queue. We next will go over to Spark in your environment here. You're working in your IDE. And what you're going to do next is basically deserialize the data, as you see here. And we're going to actually do some enrichment. So now that you're in the Spark environment, you can actually look up the zip code, as it were, in green, or map a certain ID to the kitchen appliance. Now that we have that, we actually are now doing real-time ingest, right? We set up that Kafka feed, so data is flowing in. And we're now doing real-time transformations on the data so that you are actually cleaning it up, cleansing it, getting it in good order. And the next thing we need to do is get it ready to save that data. It has to go somewhere, and we want it to be memory-oriented. So that goes into production with MemSQL. So here we are logging in to the database application. We're using the memcd database right here. And this is actually the MemSQL graphical UI. It's in the Community Edition. It's in the Enterprise Edition. But the benefit, of course, is that you can easily start looking at the data itself. In this case, MemSQL has a Spark to MemSQL connector. That's how you persist the data to MemSQL. What you do here is basically hit a command in your IDE, rdd.save to MemSQL. And behind the scenes, that will actually create an insert command that will persist that data itself. So what we did up there is just explain the devices with names table. You can see there's house ID, device type ID, zip ID, and name. And then we just did a count star on that to determine that we have data flowing into the system. Now, the best part about this is that because it's a SQL interface, it's incredibly familiar to everyone, and it's very easy to build applications with it. Moreover, you can actually immediately connect it to a business intelligence application. In this case, you can compress your development pipelines because you have the data now flowing in through Spark and Kafka and into MemSQL. And in this case, one of our partners, Zoom Data, basically can connect to our database and then start rendering results about what's going on with the hot tubs or the well pumps, et cetera, and what it's costing all of the consumers here. So the notion here is that you want real-time, immediate data to go in. And once you have that available, you can start slicing and dicing that data very easily. So it's very critical to work with data in the moment with real-time information. And what we're just seeing here is, again, basic information about the city, but it's all in real time. It's being updated live. In addition to Zoom Data, you might actually also connect it to Tableau. And in this case, what you can build are real-time applications that let you build in a way to interact with that data very easily. So the whole notion here is actually moving away from the concept of a CSV report that lands in your inbox every morning and moving towards real-time applications that you can interact with live data. So that's an example of how in-memory technology is changing the game in the enterprise itself, not just for the public sector, which we're talking about today, but really the private sector as well. The ability to build real-time applications is very critical when you want to outcompete your competitor, for example. So this notion of building interactive applications to manipulate data, to slice and dice it, is very critical when we think about in-memory technology. And it's actually one of the primary use cases, as we'll see. So we've done all this. We've built this application. And the reason why this is so critical for the smart connected city is because we can optimize urban planning. We can look at efficient power consumption, efficient transportation, and build and use sustainable energy practices. The reason why, of course, as I mentioned earlier, is that we have so many people in cities today. More than half of the human population on Earth resides in a city. So when we think about how we can leverage technology to help 3 billion people going to 4.5, 5 billion people, it's critical that we think about how we can design cities more effectively and more efficiently. So that's just a high-level example of how a smart connected city works. And we can now jump into sort of the more fundamentals about what goes into building a real-time data pipeline. Fundamentally, of course, we believe creating real-time pipelines should be push-button easy. The whole concept of an ecosystem that has a lot of complicated parts only slows down development. And what we've done with MemSQL is really make it easy to use in a single package so that you can get immediate access to that data and start using it for any application that you might want. So it brings us to something that we actually open sourced just a couple months ago. It's available at our GitHub page, github.com/memsql, is an application called Streamliner for IoT applications. And it gives you the ability to have one-click deployment of Apache Spark, which is very, very handy when you want to get started quickly. And you can basically get Spark moving faster by combining it with Kafka, as we'll see. So the whole notion of Streamliner is that we don't want to make this complicated for everyday users and end users to use. A GUI pipeline setup, for example. You can click that pipeline right there and create a new way to consume data into the system. You can have multiple data pipelines flowing through. And the whole concept of like, gee, how do I merge multiple data streams together becomes trivial when you can just do a basic join. So if we can basically look at an interface that is already familiar and map that to different data streams, suddenly it's very easy to start working with real-time data. And of course, that's all around real-time transformation. But if we look at sort of what justifies in-memory technology fundamentally, it's the fact that we can eliminate ETL from a business itself. For example, you might look at a batch process and realize that it takes 12 hours to load the data. So any query that you execute against that data set is now at least 12 hours too late to affect the business. A lot of database technologies, even in the ecosystem of Hadoop, are focused on reducing query latency, query execution latency. But really, the biggest improvements you can derive are reducing data loading latency, meaning that the faster you get access to the data, the faster you can start making insights, and the faster you can start responding to your business. So the whole notion here with Streamliner is that you can actually reduce the data loading latency to 0 and start manipulating data. From an architectural perspective, it's a very simple deployment process. You start off with a raw cluster. The next thing you'll do is deploy MemSQL so that you can actually have a database cluster running in your environment, whether that's on-prem or in the cloud or even your laptop. We actually have an ability to run what's called a cluster in a box, which gives you literally what it says, a cluster in a box. The next step is that one-click Spark deployment. So you basically now have two processes on these servers co-located. You have a MemSQL process and then a Spark process on the same machine. The benefit of this is you can basically avoid an extra network hop. Of course, you can run your own Spark cluster elsewhere. And certain times, it's actually a good idea to separate your database cluster from your Spark cluster. One of the primary reasons is that if your Spark cluster crashes and it's on the same machines as your database, well, what happens is you lose both your database cluster and your Spark cluster. So for certain use cases, it makes a lot of sense to separate. But for convenience and for basic exploration, of course, using Community Edition to do that, it makes sense to just basically put everything on the same machines. The next thing that happens, as we talked about, to complete this real-time data pipeline, is to connect Kafka to each node in the cluster. The benefit of this is that this is a multi-threaded, highly parallelized write into the system. And again, what you're seeing here is memory to memory to memory. And then behind the scenes, MemSQL does the disk in the background. So it's very exciting because there's no slowdown on this data as you're consuming it. What we'll do next is actually look at what Streamliner is. From an information perspective, Streamliner is actually an application inside of Apache Spark. It gives you an ability to ingest that data, as we saw. You can subscribe to Kafka. Because it's open source, you can build your own extractors and other data sources. And it's very easy to kind of attach the product to new data sources you want to consume. But fundamentally, what Streamliner is about is reducing ETL time. And there's an extraction phase, a transformation phase to clean the data up, and of course, a way to store that data permanently inside of MemSQL. Of course, all of this is open source, so you can hack it, look at it, see what you want to customize around it. But we really think it's valuable because, as I mentioned, it's all about taking that data loading latency to 0, not necessarily looking at purely the execution phase of the product. So if we go into the application itself, it's called Streamliner. We can dive in really quick. It's all focused around an extraction phase. So what you'll do here is actually basically paste your Kafka URL into the browser. You'll declare a topic right here. And at that point, you basically are good in business to go to the next phase, which is actually more complicated if you want it to be. But what we just did is basically attached the database to a Kafka feed. The transformation phase is really critical because it lets you clean that data. Now, you can emit it as JSON, as CSV, and you can even emit it as a custom jar. You can basically structure it however you want. But what you're going to do is you're going to define a column name here. We'll just call it data. And now you have JSON data going into the system. The loading phase is really simple because you just create a database or declare the database you want below, give it a table name, hit enter, and you're done. So what we've done here is graphically give you a way to get real-time data into a database with a few clicks of a button. This is phenomenal because now you can actually start working on the real part of data science, which is understanding what that data is saying. And this is touching on something that is broader, even more than in memory. It's about extending analytics with what is called a Lambda architecture. And a Lambda architecture is that little diagram there, which is that you have a fork in the road in your business, where you have your current existing batch processing systems like Hadoop, systems like Teradata or another data warehouse. And the goal here is that you have certain analytics that can take their sweet time. You want to run a quarterly report, a yearly report, it can run overnight. But what we're doing with this Lambda architecture is enabling a real-time data pipeline going into the system so that you can actually manipulate the data very quickly. Now, there are certain industries that really care about this on the right-hand rail. I think anything where arbitrage is critical is very interested in Lambda architecture. So if your business is focused around information, using in-memory technology is critical to outmaneuver and outcompete in the marketplace. As I mentioned earlier, with Lambda architecture, you can get analytic applications, not Excel reports. An Excel report will come out of a data warehouse, and it'll arrive in your inbox. An analytic application is live data for you to analyze. And of course, it's all predicated on real-time analytics, the ability to look at live data and actually change the outcome. The notion of just getting a faster query is nice. It might save you a cup of coffee or a trip around the block while you're waiting. But the real benefit here is that you can leverage that analytic to respond to the business, to respond to the user, to respond to the market. So real-time analytics has an ability to change the game and how businesses move, because if you move faster than a competitor, you're going to outcompete them in the long run. So in-memory databases rise up. Why? Well, to kind of brief you guys on what's happening with hardware, it's now possible to get multi-terabyte on commodity hardware. Samsung just announced a 128 gigabyte RAM chip, a DIMM slot, just this week. Imagine 2 or 3 of those in a single server and multiply that by 10 or 20, and you're now talking about terabyte scales of dozens of terabytes that allow you to manipulate data. And it's not very expensive anymore. The whole notion here is that anything in big data should be leveraging commodity hardware, 2-socket servers. If you move up to 4-socket or 8-socket, you're getting more exotic. And now you have to talk to your CFO about why you need a multi-million-dollar machine. Again, coming from Facebook, the whole notion was how can we leverage a lot of commodity hardware to scale the business. Same problem in every business that has scaling challenges. The question is, how can you get access to technology that lets you do that without having to reinvent the wheel? And of course, as we look at data science, it's important to store the state of the model, to run regression against it, to run trend analysis. So if you're ingesting data and not storing it, and with the results of that data, you're losing a key aspect about what happened to the business itself. So storing the delta is in many ways as important as storing the base. And of course, as I mentioned, it's all about building applications. You do not want to be thinking about Excel reports or outputs of that nature. How can you empower your organization with real-time technology? And of course, again, it's all about avoiding disk at all costs. MemSQL does it by doing a sequential I/O transaction log in the background. So all of the random reads and writes happen in memory, and then you get a nice continuous write to disk with the MemSQL database. So it goes beyond, though, in memory. We have to remember that not all data is created equal, and certainly all data itself is less valuable as it ages. Data from a year ago is not as relevant as data from today. So we have to look at a comprehensive architecture to both handle transactions and the analytics around that. So the first aspect, as I mentioned earlier, is the notion around real time. You need in-memory technology to go real time, and you want fast updates to quickly update the data itself. Now, MemSQL does that with its row store in memory. The next phase is how can we actually look at analytics both in the in-memory component, but also look at it from over time. So what we offer is something also called a column store, which gives you the ability to compress that data on disk. And this is perfect for historical data because you're not updating it. What happened a year ago is probably going to stay the same. You're not going to change the data too much. And this is reflective of the current generation and last generation of MPP databases that only focus on this aspect. What really kind of ties it all together is a single execution engine up top that spans the data spectrum itself. So you can go from T0 to T365 quite easily and still maintain economic price points that make sense for any given business. Another way of saying that is some businesses might need 20 terabytes of data in memory, but others might only need 200 gigabytes, 20 gigabytes. And you might have a lot of data across the entire application, maybe 50 terabytes or 1 petabyte. You wouldn't want to put a petabyte of data in memory unless you were maybe a government entity. But you can put 1 petabyte of data on disk. The cost of disk is 0. So the whole component here is tying it all together with a system that can handle in-memory processing, real-time analytics, and also store lots and lots of data. Because again, what happens when data in memory decays? You have to move it somewhere. You either delete it or you move it to a data warehouse. An easy way to deal with that in MemSQL is just to insert select into the column store. So we have a simplified Lambda architecture with MemSQL here. There's a Lambda architecture is comprised of 3 tiers: a batch tier, a speed tier, and a serving tier. And what we have is fundamentally a Hadoop as a traditional Lambda approach. The alternative, if you structure the data a bit, is to use the MemSQL column store. Now we also have that speed tier. Again, Storm and Spark are great examples. And as I showed you earlier, Kafka, Spark, and MemSQL is an equivalent way to deal with the speed tier. And then when you serve it, moving away from NoSQL, Cassandra and HBase, they let you serve the data, but again, you can't analyze it. And again, the whole component here is use MemSQL to avoid the NoSQL follies. Lambda certainly applies to those real-time data pipelines. We have inputs, we have that message queue that we already looked at, and we already talked about how you batch it and go real-time. So what we saw earlier was this process. To take it into a real example, Pinterest is a customer of ours that uses this real-time data pipeline technology. And they're actually putting 1 gigabyte of data per second into MemSQL. That's 72 terabytes of data a day. A phenomenal amount of data flows into the MemSQL database in this particular application. But the whole goal was that previous to this, they were seeing a 24-hour blackout period with Redshift. So if you're loading lots of data into Redshift, you can't touch it until it's loaded. Similar problem that Pinterest had. We'll see that again and again and again. When you actually want to get access to the data, loading it first and then analyzing it is very, very slow. You can get access to it instantaneously. You now have a game-changing technology advantage. Another example would be Tapjoy. Again, they're using this for real-time personalization. Over 60,000 queries per second are going into this particular use case with millisecond response times. Again, you see that similar Lambda architecture. You have Kafka that forks it into Spark and HDFS and Vertica. And then the real-time analytics themselves come out of MemSQL. So this is very exciting because you're not actually replacing your existing infrastructure. You're extending it. You're enabling it with new technology. Comcast is a great IoT example. They were just using Hadoop before. They were seeing 30-minute latencies per query. And a lot of other problems, really, that no one can easily use MapReduce, right? So any data scientist or business analyst that wanted a new query would have to go to engineering and say, can you get this MapReduce job into the system? We took them to sub-second access with a SQL endpoint by giving them in-memory access to that data. The reason why this is an IoT use case is that this is tracking every Xfinity box in America, similar to a cable top box anywhere. It tracks telemetry, bitrate health, what's being watched at any given point in time, so that they can optimize their business and understand what's going on with their network itself. Perhaps there's a performance issue in one part of the country that they want to analyze and look at before customers complain. So with in-memory technology, it's all about going from a reactive state to a proactive state, if you think about it that way. We can look at another application that is also interesting. We can analyze Twitter data in real time. In terms of how this works, you can connect to a public API, the garden hose, use some Python to stitch it together and get it into the Streamliner application. What we can do is install MemSQL and Apache Spark in under a minute. This is something where we can install using ops or run a command on the command line. And it's a little hard to see, I know, but what we're doing is effectively now downloading MemSQL and just getting it ready to access. So again, you can access this binary off our website or our GitHub page. And the whole goal here is that you now have something running and easy to use. We love Docker. So even though MemSQL is only engineered for Linux, you can actually run MemSQL on your Mac laptop using a Docker container. Also, you can run Kafka in a Docker container as well. So you might have a Twitter topic here that we're subscribing to. We're now basically spinning up the Docker image. We created the Twitter topic. And the next thing we have to do is start subscribing to it. So we can let that run for a bit. But the whole notion here is that we actually have data ready to go. So as I showed you, this is actually a graphical example of that process that we went through a little earlier, where we just paste in the URL of that Kafka feed, declare the topic Twitter, data, and the database and table name. The beauty of this is that we're not doing any DDL. We're not going through the pain of defining a schema. Now you might ask, well, how is that possible with a SQL database? Well, the answer is that we have JSON in the database itself, so you can basically put semi-structured JSON data in and use SQL to traverse and analyze it. Super, super punchy feature. It lets you do something like this, where you can basically get a live data feed into the system very quickly. Then you can use a Python script to load tweets into the Kafka topic, get data flowing. Again, this is something where, as a toy application, very straightforward. We now have that ready to go. And we can move on to how to basically connect to that system. Again, the whole notion here is that we're going to run a count query. It just shows you that data is flowing in. We run that again. It's incrementing upwards quite quickly. But we now have real-time live data going into an easily accessible database. There's the table itself. So as I mentioned, you get this power of SQL and JSON together. You can join, index your JSON data without actually having to touch it. So it really combines a lot of different concepts in big data into an easy-to-use interface. Now, you can also do online alter table. When we think about how we can basically run real-time applications, they tend to be more operational and online. So in this particular instance, you want to use an alter table to change the schema. But most other databases, you might have to lock the system. You might have to turn it off. With an online alter table, you can actually extend the schema without taking anything down. So that's very critical. So this is just an example of how we're actually running the queries here. This will be easier to see in the webcast if you want to log back in. But the interesting thing, of course, is that with Streamliner, you have an ability to group your Spark jobs and Spark workers more effectively. So basically, any Spark worker in Streamliner can access any driver. Whereas without Streamliner, you have to create multiple Spark workers that can only map to their correct pipeline. So using Streamliner is a phenomenal way to actually use your resources more effectively. And again, it's on GitHub. Check it out. So as we wrap up, I want to talk a little bit about what's next. So we talked about the connected city, how you can use it to actually optimize and build sustainable practices. But the next phase of that is how can you predict what's going to happen? And I think that's the most interesting part about in-memory technology, is that once you get live real-time data into the system, you now have an ability to say, what if? What if this happens, right? And you can do that by creating a custom model. This is taking your data science chops and putting them online. We just lost a transport there. Let's see what we have. Bring that back on, perhaps. Reconnect that. And while we're bringing that back online, I can just talk about what it means to build a scoring model. You might use SAS, you might use R, but the real benefit of using a model in real time is that you can pump real-time data through that model, and then out comes a score. So that score gives you an ability to effectively understand what's going to happen in the predictive side of the application. The slide that I'll show you, again, we'll put it back on the webcast, is basically an ability to interact with that data and work with it in real time. So to conclude, we have a community edition of MemSQL. Feel free to go to our website, memsql.com/download. Go to our GitHub page and check out Streamliner. But the real benefit of it is that you can start manipulating data quite easily. Also here at the conference, we have a O'Reilly ebook and physical book entitled Building Real-Time Data Pipelines. Would encourage you guys to pick up a copy of that. And now we have a few minutes for questions. So thank you guys very much. It's a pleasure to be here, and I hope you enjoyed the presentation. I'm also glad that happened toward the end of the presentation, like not right in the middle. So any questions whatsoever while we have a few minutes before we wrap?
You mentioned that the schemas are automatically created, right? Because you have JSON coming in?
Correct.
Right. So in JSON, you could have certain attributes missing, right?
That's correct.
One JSON could have an attribute missing. So how are you guys dealing with that?
Yeah, so what you're doing is actually taking the JSON object and putting the entire object itself into a column. And then that column will store the data as if it were blob data. But in this case, it's a more intelligent way to actually access that data. So you can use a SQL query to basically traverse a hierarchy, a nested hierarchy of attributes. And if a value is missing, you would find it. Or if you were trying to access an attribute that wasn't there, the query just wouldn't complete.
Good afternoon. Do you have any other use cases besides report analytics, like financial or?
A lot. So the question was, are there any other use cases beyond real-time analytics? Absolutely. The whole notion here of user data in ad technology, real-time segmentation, real-time bidding and attribution. Within financial services, you might see something around real-time risk management, real-time streaming data into the system. We have other customers that are using us for billing engines, real-time billing. Akamai is a customer, for example. So the whole notion is, how can you actually manipulate data consistently? And if you can manipulate data without consistency, you probably don't need a database like this. But if you care about user data, for example, typically consistency is ultra important. So those are a few examples where we work. Yes?
So what are the main difference between MemSQL and other tools like SAP HANA?
Yeah, it's a great question. The question was, what are the main differences between SAP HANA and MemSQL? There's a number of them. We focus on actually scaling on real commodity hardware. SAP HANA is really more of a vertically scaled approach. It is not really well suited for cost-effective deployment. You might look at a HANA box as being $1 million north, whereas MemSQL you can run on your laptop and extend it with multiple servers. Functionally, the row store in memory that we offer is going to be different than any in-memory columnar technology. And we find that you can put columnar on disk quite readily. And using columnar in memory solves the query execution, certainly, but it doesn't solve the query loading, the data loading. So those are just a few examples. I could talk my head off on it, but probably only a couple points is worth it. Yes? In what industry?
Just any clients.
Sure. So the question was just sort of what is the customer profile of who uses the technology, of who uses MemSQL. A lot of banks use the technology. Certainly, web scale companies like Uber and Pinterest. It's definitely oriented for high performance database solutions, and we work with companies primarily in the Fortune 1000 and beyond. But with the fact that we have a community edition, we have a lot of startups using the product as well because it's just free and available and no limitations on the product. Yes?
If MemSQL is not running on the same cluster where Spark is running, what does the architecture look like? Does it need another Kafka? Does it need to go through?
Yeah, it's a great question. So the question was, what happens if you run your Spark cluster separately from the MemSQL cluster? It's basically just a connector between the two clusters. So you would have Kafka going into the Spark cluster for manipulation. And then inside of your environment there, your IDE, you're going to issue a command to push that data into MemSQL. Conversely, you can also extract data from MemSQL and put it into Spark. So it's a bidirectional connector that lets you both push and pull data into Spark.
Thank you.
Any questions on smart connected cities? Sure. Oh, we have one over here first.
Okay. Sorry, can you share some benchmarks in terms of the performance, and where do you see the bottleneck actually from Kafka to Spark to MemSQL?
Sure. So the question was, what are some performance benchmark information? High level, a very basic server can do about 500,000 inserts per second very easily. The reason why, and I mentioned this earlier, is that with in-memory technology, what you're doing is disintermediating the disk from the application. So what happens inside of MemSQL, we didn't touch on this, is that there's a background process that is doing a transaction log as well as a snapshot, a periodic snapshot of the state of the system. What this means is that disk is being controlled very efficiently with only continuous I/O. Moreover, we actually don't have to write an index to the log. So the log itself is actually skinnier than a conventional disk-based log. So when we recover the database, let's say you actually have a data center outage, you're actually reconstituting the indexes as you load the data from disk into memory. The other thing, of course, with the product is you want to have your data in two places, so that's possible with redundancy level 2. You just basically get a second copy of the data on the same cluster, and then you can use cross data center replication to move that data to another data center for total safety and disaster recovery. Oh, so the question I think was seeing the code. Yeah. So all of that code is actually available on our GitHub account. So go ahead and check it out. It's basically available for easy downloading on the GitHub side. And I want to make sure we're actually running up on time. I'm getting that buzz. What was the question? So the question was, how do you get access to the software? So as it stands today, MemSQL actually packages Spark with MemSQL, so you get both. And then it would be up to you to basically connect it to a Kafka server. Very easy to set up in terms of installing the process, but we believe the faster you can get it up and running, the better. So I hope that answers the question there. Perfect. Well, thank you guys. It was a pleasure being here. Hope you enjoyed it.